currently under review for publication in the quarterly journal of Royal Meteorological Society, Alberto Martilli and Francisco Salamanca. Okay, so as we've seen, the interaction between winds and urban environments is usually understood as a frictional one because urban environments introduce, with a distinct morphology, greater roughness into the natural landscape, and they accept the drag effect of wind flow that depends on characteristics like building height and building array density. However, urban environments also introduce thermal modification to natural landscapes, and several authors have observed that the pressure gradients associated with the urban heat island effect is able to promote inflow from the surrounding rural areas and induce a local circulation characterized by low-level convergence and upper-level divergence. In complex terrains, and most cities are located in complex terrains, further complexity is added to this interaction, to these dynamics, because in the absence of strong synoptical forcing, complex terrains are characterized by their own local circulation, the thermo-topographical circulation, which is driven by heat exchanges between the land surface and the overlying atmosphere, and is characterized by upslope and up-valley wind flows during the daytime, and downslope and down-valley wind flows during the night. Despite the potential implications for societally relevant issues like air quality in urban environment, thermal comfort, and aviation operations, the interaction between local circulations in complex terrains and involving urban environments has so far been rather limited. So that motivated me to explore more what was going on in the city that hosted my PhD studies and to formulate the following research questions. How does the Phoenix urban boundary layer interact with the thermotopographical circulation? And is the Phoenix urban heat island able to induce a distinct, well-developed circulation? And if so, how does that interact with background complex terrain wind flow? In order to answer to these questions, I developed two numerical simulation experiments based upon the following scenarios. The control one, where the landscape within and surrounding the Phoenix Metro area is realistically represented using the 2019 version of the National Land Cover dataset, and an hypothetical pre-settlement scenario where all urban and agricultural pixels are replaced by the dominant land cover category represented by the shrub vegetation, and also all urban fraction has been set to zero everywhere. So using these scenarios, I ran two WRF simulations coupled with the PEPBAN multi-layer model, and using a one-way three-nested domain configuration with the innermost domain having a 1 kilometer grid spacing. Both simulations were forced with data from the North American Regional Analysis dataset, representing climatological conditions for the summer of 2020, which was one of the hottest and driest of the last 30 years. That was meant to avoid compounding effects connected with convective storms typical of the North American monsoon season. I evaluated my simulation results against a suite of 5 urban and 4 rural weather stations, and that showed that our configuration of the WRF model did a pretty good job in representing 10 meters mean wind speed. Fortunately, that was not the case for 2 meter air temperature. As we can see, we had a pretty strong and prolonged nighttime cool bias. We tried to address this issue like improving the representation of the urban fabric and changing especially the volumetric heat capacity values for the urban surface. Although effective, these modifications didn't prove to fully fix the bias, and we'll see later on how these may provide some limitations to our results. So, nonetheless, the model in our configuration was able to correctly represent the near-surface daytime cool island and nighttime heat island that is previously described for the area by several authors. And furthermore, the model was also able to correctly reproduce the alternation between the southwesterly anabatic wind regime of the daytime and the northeasterly katabatic wind regime of the nighttime. Here in this animation, we can see that Phoenix definitely resides within a complex terrain. The color shading represents the topography of the area. This is the innermost domain. And the black outline represents the extent of the Phoenix Metro area, just for reference. So, to the first research question, how does the urban boundary layer of the Phoenix Metro area interact with this thermo-topographical situation? As we can see in this video animation representing summer average hourly wind vectors for both the control scenarios represented by black arrows and by summer average hourly wind vectors from the pre-settlement scenario represented by the red arrows, the Phoenix Metro area exerts mostly a drag effect on the background wind flow, especially during the nighttime, as shown by the green areas of the color shading in this animation. However, this drag effect becomes very weak and almost negligible during daytime, and we found that a possible explanation is due to added mixing, turbulent mixing, and a deeper boundary layer in the nighttime, as shown by the increase of the excess of urban sensible heat flux during the daytime, represented by the red line in the top panel. So, for example, at 6 a.m., where the excess of sensible heat flux over the urban area, considered as the difference between the control and pre-settlement scenario, is only 7.2 watts per square meter, and the urban boundary layer is only 86 meters deep. In these conditions, the background wind flow experiences a wind deceleration of 45.5%. So the original wind 2 meters per second wind is reduced by 0.75 meters per second. At 2 p.m., when the excess of urban sensible heat flux reaches 131 watts per square meter, and the boundary layer is almost 2,000 meters deep, the wind deceleration exerted by the city is only 10%, 10.4%. Sorry. So, on to the next research question. Is the Phoenix urban heat island able to induce a distinct well developed circulation, and how does that interact with the background complex terrain wind flow? So the short answer is no. We don't find any evidence of a proper urban heat island induced circulation over the Phoenix Metro area during the summer of 2020. However, the impact of the urban heat island of the Phoenix Metro can be perceived in a sort of modulating effect of the background wind flow. So, contrarily to what I showed you earlier about the near surface daytime cool heat island, at 25 meters above ground level, which is the mass center of the first model level, the Phoenix urban boundary layer exhibits a weak but clear urban heat island effect, and this is able to interact with the background adiabatic wind flow, creating areas of slight wind increase upwind of the city and areas of slight wind decrease downwind of the city. During the nighttime, despite a stronger urban heat island effect, we can only see impacts on the background wind flow along a narrow band located at 33.4 degrees north latitude, which is a region where the downtown Phoenix is located and also the Phoenix Sky Harbor is located. So it's a very densely urbanized area. It also lacks in morphology elements on the west part of the city. So here, the combination of the strong drag effect on the easterly katabatic flow and the promotion of a weak westerly flow, here represented by this gold patch on the western part of the area, is able to shift the center of air mass convergence eastward by almost 10 kilometers in the control scenario compared to the pre-settlement scenario. And this is the only impact that we've been able to see from the nocturnal urban heat island on the wind circulation in the valley. So in order to wrap up, the Phoenix Metro area exerts a strong drag on wind speed during most of the diurnal cycle, but this drag effect is extremely reduced and becomes almost negligible during daytime, due to increased turbulent mixing at deeper boundary layer connected with the excess of sensible heat flux over the urban area. We don't see any evidence of a well-developed, distinct urban heat island-induced circulation over the Phoenix Metro area, although this might be the result of an underestimation of the nocturnal heat island, as shown by our model simulations evaluation. However, the urban heat island over the Phoenix Metro that is actually reproduced by the model is able to interact with the background wind flow circulation during certain times of the diurnal cycle, and it is by creating areas of upwind acceleration and downwind deceleration during the daytime, and by shifting the center of air mass convergence 10 kilometers eastward compared to a hypothetical pre-settlement, no urban, no anthropogenic scenario. And with this, I will thank you for standing so long to my talk and my. Thank you. Thank you.
Thank you very much, Aldo. 3 minutes left for questions, please. In my back again.
Sorry. Thank you for the presentation. I was wondering these thermal flows, the adiabatic, katabatic flows, how deep is it in relation to the boundary layer height?
They extend also above the boundary layer height. So, for example, yes, in this situation, for example, I'm only showing the control simulation wind vectors, because basically in the no urban, in the pre-settlement simulation, the wind vectors are identical. So I didn't want to add further mess to the figure, which is already pretty dense. But basically, although we can see here some updrafts, these are basically the results of the collision between opposing flows rather than something triggered by the heat coming from the city.
Thanks.
You mentioned about the potential underestimation in the UHI circulation. Was there any observational evidence that did you do any measurements there? Like actually what is the UHI in the Phoenix area and during the simulation time?
No, I didn't do that because that happened in 2020, which was rather difficult year to do any. But actually, our results were pretty consistent with those of previous works published investigating the area. So yeah, I did a comparison with the literature because at ASU we have plenty amount of research in the area, and so yeah, they were consistent with previous works.
One last question. Anybody has something?
Could you suggest another city than Phoenix? Like that would be of interest because so many people look at Phoenix, but at one point, no? Is there something else?
Las Vegas.
Las Vegas is a one city.
It's just city.
It's not a city. It's just
Yes, actually, there's plenty of other cities that could be of interest because many cities are located in complex terrain. And currently at EPFL, I'm investigating the wind flow and interaction with the urban environment for the cities of Lausanne and Geneva. But I just started there in May, so it might take me a while before I can present the results. There's also further complication due to the presence of the lake. So there's also sort of a sea breeze effect that will have to be taken into account. But I will also specify that Phoenix is a rather peculiar case because the urban fabric is constituted by pretty short buildings that are very far from each other. So it's a pretty sprawled area and not that dense. And that's the reason why I included this figure in the first slide, because that's exactly the situation in Phoenix. So there's like low buildings far from each other with exerts a very strong drag effect, which might explain what we see in the results of these simulations.
Thank you very much. We have to move on, I'm afraid. I had a question on the nighttime bias of the model, but I think that needs an hour of discussion or even more. Right. Okay.